Hey everybody, welcome to the DNews NASA JPL monthly Space Out. We get together with some people from NASA JPL and we talk about space and technology. We talk about the future of planetary science. I'm Trace, and with me today is DiscoveryNews.com space producer Ian O'Neill. Hey Ian.
Hi Trace, thank you very much. And today with us, we are very lucky to have three esteemed guests, all world leaders in atmospheric science. First of all, going from my side, from left to right, it's probably different for the viewers, but we've got Annemarie Eldering, Deputy Project Scientist for the Orbiting Carbon Observatory-2. Then we've got Howard Eisen, ISS-Rapidscat Project Manager. Then we got Josh Willis, he's JPL Oceanographer and Climate Scientist. And I just really wanted to ask you guys, just give you a little brief introduction to what your work is and what your science is and what your missions are really about and what really gets you excited about this field. Starting with Annemarie on that side.
All right. Thank you, Ian. So you are talking to me at one of the most exciting times in our project. We are about to launch our satellite into space. We are actually going to get the OCO2 satellite into space early Tuesday morning next week, so just 6.5 days away. And this is, OCO stands for the Orbiting Carbon Observatory. We're going to measure carbon dioxide all across the globe. And it's a piece of the puzzle about climate change that we don't have all the information we need, so I can tell you more about that today. And I'm the Deputy Project Scientist, so my role is to help coordinate and organize many team members that make the data turn into the science and the science products that we deliver to the public.
Cool.
Sounds very exciting. Okay, Howard.
Hi everyone, good afternoon or good evening depending on where you are. I'm Howard Eisen. I'm the project manager of the ISS-Rapidscat payload. Our name starts with ISS because we're located on the International Space Station, and the payload name is Rapidscat because it's a rapidly developed scatterometer. Scatterometer is an instrument that basically measures winds on the ocean from space. So we get the direction and speed of ocean wind, but we do it by sending a radar wave from the space station down to the ground, and it bounces off the waves, comes back up, and is captured by the satellite. In this case, by the instrument which is mounted to the space station. That means we can see pretty much anywhere the space station flies, which is 51 north to 51 south. We can see what's going on down at the ocean surface and understand the wave speed and the wind speed and direction. This is a follow-on to a prior mission called QuickScat that has been measuring this type of information since 1999. Today I'm in Florida at Cape Canaveral. We just finished completing integration of the payload. It is all prepped and ready for installation into our launch vehicle, which is a SpaceX Dragon, and that installation will occur this week on Thursday.
That sounds really cool. So you're basically just latching this thing onto the International Space Station and using that as a ride to see the whole planet.
That's right. The SpaceX Dragon takes us up, and we use the robotic arms on the space station to install us. And then we get to live permanently on the outside of the space station until that space is needed by another payload in 2 or 3 years.
Very cool. Okay, over to Josh.
Yeah, my name is Josh Willis, and I'm the project scientist for the Jason 3 mission, which follows on Jason 1 and Jason 2 and measures the height of the ocean from space. And I'm trained as an oceanographer, as you said earlier, and the height of the ocean from space is important to us because it tells us about the currents in the ocean. Whenever there's a big current in the ocean, it tilts the sea surface, and we can actually measure that tilt using the Jason satellites. But the Jason satellites do something else which is really, really important. They actually measure global sea level rise. As humans emit carbon dioxide into the atmosphere, as we change the composition of the atmosphere, we trap extra heat on the planet. Most of that heat warms up the ocean and causes thermal expansion. That contributes to sea level rise. And of course, the melting of the glaciers and ice sheets also contribute to sea level rise. So our mission measures all of this stuff together, and it comes up with one single number every 10 days. And we can actually use this number to chart how much humans are changing the planet's climate over time. And as we look back over the last 20 years, we've added about 6 extra centimeters of sea level to the oceans. Now, that doesn't seem like a lot, but you got to remember 2/3 of our planet are covered by oceans. So this is a huge extra volume of water we've added to the Earth's oceans. And that's what we measure from space with the JASON satellites.
So really, all you, because bearing in mind I'm space producer, so I'm always looking up into the stars. I very rarely take time to look back at Earth, and I always found atmospheric science extremely complex and very dynamic. So all your missions kind of are intertwined, and it's like you're reaching this point where you're all kind of meeting, and you're all going to be looking at heat flow around the planet. You're looking at how heat is transferred from the atmosphere to the ocean, sea level rises. How does this excite you? I mean, this must be a thrilling time in your careers.
Yeah, absolutely. I think, especially in terms of looking at changes in the climate and changes in the ocean, humans, we often say, are running an uncontrolled experiment on the only planet we have. We're really driving our planet's climate, and now human beings are the biggest driver of climate change on the planet. And missions like these, really all three in different ways, give us a careful look at just how our planet's climate is evolving. And for example, the JASON satellites to me are really exciting because sea level rise that's global, that we can see in the entire volume of the ocean, is basically irreversible. So in a lot of ways, we're measuring the irreversible changes that we have wrought on our planet's climate. And it's exciting from a scientific point, and of course it's a little scary from a personal standpoint.
Yeah, I bet. I mean, I was going to ask early on, what's the importance for NASA, which is mainly considered a space organization? So anybody can answer this, but other than, why is it important to look back at Earth? And I think you nailed it right there. The importance is we have to see, I'm guessing, like our impact, and we have to be able to measure that so we know what's going on. Is that, Annemarie, would you say that's pretty accurate?
Yeah, I was going to pipe in and let you know that for a lot of the science questions we're answering these days, we have some data sets that are made from surface-based measurements or flying airplanes around, but it's limited. What we can learn is limited by that. And what our mission seeks to do is get measurements across the whole globe. So really, if you want to measure across the globe, the land and the ocean and everywhere, it makes a lot of sense to go to space and fly around Earth and see it from above. So we can capture global data. With a mission like OCO2, you'll collect data at 1 million places every day. And you'll lose some because of clouds, but still you think you'll have 100,000 pieces of data. That's orders of magnitude more than we could collect any other way on a day-to-day basis. So to unlock these puzzles of how we're changing our own planet, we need to see our own planet, and space is a great vantage point for that.
Yeah. So OCO2, for people who don't know, is the Orbiting Carbon Observatory-2. And what happened to OCO1?
Well, it is a sad story, Trace. We actually built this instrument once before, and in 2009, it was on a rocket getting ready to go into space. We started the launch, and then a piece of what they call the fairing, a shell that encapsulates the spacecraft, did not blow off properly, and so this extra weight on the rocket, on the spacecraft, caused it to fall back down in the ocean. So we went up and back on down. So we crashed into the ocean, we lost the whole thing, and there was a lot of work then to explain why the science was still really important, and that's why OCO2 is a carbon copy of this carbon measuring instrument.
Is that a pun? That was good.
Yeah.
Did you have a spare? Did you have a spare satellite just in case this happens, or did you have to build the whole thing from scratch again?
We had to build everything from scratch again. That's why here we are 5 years later, and we have this brand new build of the instrument, a new build of the spacecraft, a new rocket to take us into space. And we're a little smarter. We do have a spare instrument, so God forbid something didn't work right, we're a little bit ahead of where we were last time. But yeah, it took quite some time to get it all built back up again.
Yikes. Well, it's going to go better this time.
Don't get me on a downer note, man. We got 6.5 days to get into space, and everything
know,
is looking great. We're very, very,
The
very,
launch
very
is on
excited right now.
July 1st. The launch is on July 1st, right?
Correct.
Cool. And what time?
So if you're out here on the West Coast, it's 2:56 in the morning. So
Oh.
we need to go at this crazy hour because we're going to line up with a bunch of other satellites that are already flying around. So we have a 30-second window to get up into space on the 1st of July. So it's,
Awesome.
yeah.
30 seconds.
Yeah, that's why they do a countdown, man. It's a
I
lot.
can barely get to meetings on time, and you have to get to space on time.
Well, the boss said we have to be in our seats 4 hours before that because I guess he doesn't want us wandering around at the cafe.
Oh. No sandwiches in mission
No.
control, huh?
No.
So, Howard, why don't you? I'm interested in the ISS-Rapidscat because I was reading up on it, preparing to hang out, and they were talking about QuickSat and how Rapidscat is replacing QuickSat.
Sure. So we have a history of trying to build these scatterometers. We built one called Seawinds, which was an instrument that we put up twice. Once on a Japanese mission called Adios, and unfortunately it went adios, and that mission didn't last very long. They had a power problem, and that spacecraft died. QuickSat was launched in '99 on a spacecraft, and it worked fine for 10 years. From '99 to 2009. And in 2009, the spin mechanism, which spins the antenna around, stopped working. And so the radar can still work, but if you can't spin the antenna, you can't get all the information you want to get.
Right.
But back then, when they built the instrument in '99, they built what we normally do, which is they built engineering models. These are early models of the instrument parts to make sure that everything's going to work right. And it's not all of the same quality as the flight hardware. Some of these items were spares, and they were the same quality. Others were test units. And so what we did is, when we found out there was a chance to put an instrument up on the space station, we went and collected up all those spare parts that were laying around. And it turned out there were enough spare parts from these two instruments that were built in the late '90s to put together a new instrument. And so most of our hardware is between 17 and 20 years old. And then what we did is we built some new interfacing hardware because the space station looks different to the payload than the spacecraft that we were hosted on before. So we had to make some power changes, and we had to build some new computers and other things like that, and some new structures to adapt it all. But because we had an instrument, and because Space Station provides us a free launch on a Falcon up to the space station, and because they, once we're up there, give us power and attitude control and all the other things a spacecraft can do, we're able to pull this mission off really cheap. And so we put up an instrument that only cost us about $30 million. And normally, if we were to do a separate mission for this, it would cost $350 million.
Wow. Talk about reduce, reuse, recycle, right?
That's the idea.
Awesome. Yeah,
Why leave a
that's
good
really
instrument on the ground?
For sure.
I just have a question about that mission. I mean, describe to me what you say it scatters something. How does it make these measurements? I mean, what does that actually mean? What does that process actually mean?
What we do is we send a radar wave from the instrument down to the ground. And that radar wave bounces off the ocean. And what we do is we look at the back scatter. So when the radar wave hits the ocean, if the surface were completely flat, almost all the radar wave would be scattered forward, and none of it would come back to the receiver on the space station. But because the wave has some height to it, it's got some profile, that gives us surface to reflect off of and send the wave back. And so by looking at that back scatter, we can interpret that, and that height gives us an indication by the cross-section, basically how much area we see, what the radar cross-section is of the waves. We can figure out the intensity or the wind speed. And then because we spin the antenna around 360 degrees, we get that action from all different angles. And then the computers process it all together on the ground, and the result is we get speed and direction of the winds over the ocean.
That's genius. Amazing. So, Josh, I mean, with the Jason satellites, do they operate in a similar way? Do they use radar, or do they use some other method to measure the height of the ocean?
Absolutely. The The JASON satellites are actually one of the simplest satellites, simplest measurements we make. And it very simply bounces a radar wave straight down. They only look, they're nadir looking, so they only look straight at the ocean below them. It bounces back up, and you measure the time it takes to go and come back. And that tells you the distance between the ocean and the water. Then you need to know where the satellite is. So there's also a lot of positioning systems, GPS, DORIS, a little laser reflector. And you put all this information together, and it tells you how tall the oceans are. And it's interesting, you picked three really intertwined missions here because, of course, we need to know the winds because the winds tell us how the currents are flowing. Essentially, most of the currents that we see in the ocean are a reflection of the forcing by the winds, which is exactly what the scatterometer measures. And of course, OCO measures the amount of carbon dioxide in the atmosphere, and this is the primary thing that's forcing our climate change. So in a lot of ways, Annemarie's mission is measuring the forcing, and our mission is measuring the response of the Earth to that forcing. So really, in a lot of ways, we look to the oceans and things like the altimeter to say, how is the ocean reacting to these things? How is it reacting to the wind? How is it reacting to the forcing of extra carbon dioxide in the atmosphere? So,
I did have one question really for Annemarie, and this goes back to the OCO2. With your mission, what is its intent? Are you going to be looking for specific regions of the Earth where there is a lot of production of carbon dioxide? So is it as efficient that it can come over my head, over my house and say, okay, the O'Neill residents, they're producing too much CO2? Or is this more of a general mission that's going to look really for sources and sinks on a global scale rather than looking at that fine-tuned detail?
Yeah, we actually did have a question on that as well from social, so call out to Connie Wang as well. So awesome.
I'm in tune.
So Ian, in a way it may be surprising, but we still have some really basic questions to answer about the carbon dioxide. So the kind of state of our knowledge today is we know that we're burning gasoline and oil and coal, and we emit carbon dioxide from those. And we have a good accounting. Every year we burn so much fuel that we actually put about 40 gigatons of carbon in the air. And so 40 is sort of just a number to have in your head. But what happens is with the few places we measure carbon dioxide these days, we can make an estimate of what is in the atmosphere. And only half of what we put up there every year stays. Some of it seems to be absorbed by the land and the ocean. And on a global scale, we can put together this little budget. But we don't really understand which part of the ocean exactly is taking it up, which forests, which parts of the land, and every year it's a little bit different. So there's a real basic question about where the carbon dioxide is going, why is it different every year, and does it move, like, do the key regions, are they always the same regions, or are they moving around over time? So that's a question we want to answer first, or what we call a regional budget of the sources, the places where the carbon comes from, and the places where the carbon goes. As for you and your house and the CO2 you were emitting, that's a business for a day in the future. I think that's where we're headed, but we're not there yet. First the big question, and then we'll get down to the finer scale of things.
Yeah, because I've got rabbits, and I'm worried about how much CO2 they produce. So they eat a lot of grass. Thank you. Trace, you might be on mute.
Sorry about that. I was on mute. I was going to say, don't get him started.
But I heard no noise.
Yeah, I said, don't get him started talking about those rabbits. He'll talk about them for a long time.
Notice I stay quiet. I stay quiet.
It's good. I'm glad that everybody picked up on it when I was on mute. I did want to bring up, because Josh, you brought up climate change, and we did get a couple of questions from Twitter. Benjamin Gross wants to know what's the best way that people can prevent further climate change on a personal level. And I thought maybe somebody would have somebody like Josh. You want to take up on that one with Benjamin?
Yeah, sure. I mean, the thing you have to remember about global warming and climate change is that it really is a global issue. So we have to do things on a personal level. You should reduce, reuse, recycle. You should try to drive a fuel-efficient car. Don't waste water. Don't waste power and electricity. And just try and be more efficient in your use of this energy. But of course, that's not enough. We have to act at a global level as well. And personally, what I always tell people is, in addition to planting a tree and driving a Prius, you should vote for the environment. You have to tell your policymakers and the people who are, in charge of steering the global economy and the global policies to pay attention to climate change and global warming, and that it's important to us. So we can't do it by ourselves, but we need to do individual things as well. It's sort of a two-pronged approach, and both things I think are very important.
Yeah, for sure. I did want to ask too, because of the way we're measuring these things, with all three of your missions are, as Josh said earlier, pretty interestingly intertwined. Is it important that, like, Howard, your mission's on the ISS, which is pretty close to the ground, relatively speaking. Does that change? Like, if you had launched a satellite, would that change how you measured, or does it matter that you're closer to the ground?
Well, it turns out that the important thing here is to get global measurements with all of our instruments, but different instruments want different conditions. It's easy for us to be lower. We get a stronger return from the radar signal, which is important to give us good signal-to-noise ratio. A lot of other spacecraft want to be launched, like OCO, want to be launched out of Vandenberg because they want to go into a polar orbit, and their job is to stay in that kind of an orbit where the Earth passes under them, basically the same places pass by every day at around the same time. We're concentrating more on the lower latitudes in the tropics, so we get better coverage of the tropical storms.
Cool.
Hey, Trace, can I pipe in on that question too?
Absolutely, yeah.
Yeah, so it's interesting because we have OCO2 getting ready to go in this polar orbit that Howard mentioned, and we'll be, at 705 kilometers. But we're also working on a project to get the spare instrument we built and install it on the ISS. So we're going to try to build a system that will let us run that instrument much lower on the ISS at that 400 kilometers. And there were a few adjustments we had to make having to do with the alignment of the sun and our instrument, and it's very different on the ISS orbit from the polar orbit, but it's all pretty doable. Basically, you need to make a few adjustments, and the thing that's really cool about the ISS is you don't see the same time every day, so if you're interested in a process that changes over the day, you can learn about that from the ISS in a way you can't do from most of the other orbits we use. So there's benefits and costs for using both of those, but I think there's a role for both of them in our science.
That's very
that
cool.
last point, Annemarie, is an excellent one. All the previous scatterometers that we've had have been in polar orbits, and so they've traditionally looked at about 7:30 a.m. at what's going on in the winds. So we have wind measurements for 10 years now, or 15 years, at 7:30 a.m. and 7:30 p.m. We don't have any measurements for what's going on at noon or 2 o'clock. And so from ISS, for the first time, we're going to get that. That's one of our main science objectives, is to be able to find out what's going on during the day, take all those models of how winds vary, and be able to adjust them for what's going on during the daytime.
Wow. Yeah, that's a whole different thing if you're measuring only twice a day versus how many more measurements are you going to get then?
So the ISS orbit is constantly moving around. So one week we may get a certain part of the ocean at 2 o'clock in the afternoon, and then that'll move around like 20, 30 minutes a day. That time will keep marching along, and so we'll get continuous measurements just 23 hours apart kind of thing.
Very cool. So over time, you're going to end up mapping throughout the day and in a number of different locations, much more so than you had before. That's awesome.
That's right, and that'll keep the scientists busy for years.
Yeah, I bet. Let's see if we got any. Ian, do you have any follow-ups? I'm going to look at the Twitters here and see what we got.
Yeah, I did have a personal question. Yeah, I was just looking through Twitter now, but I just had one question that I mean to ask. Because, of course, carbon dioxide is a huge greenhouse gas. But are there any considerations for, like, methane or other greenhouse gases that could be fiddling with these results while you're looking at sort of sinks and sources for carbon dioxide? I mean, are there any plans in the future to be looking for these other compounds, or is that really something that's going to be for future missions to be looking at?
So it's interesting that you asked that question, because when the idea for this OCO mission was first developed, the guys wanted to include methane as part of that measurement. So it was there from the beginning, but then they had to keep the cost down and simplify things, so we didn't include the methane measurement.
That's a shame.
Yeah, the wavelength you need is not that far off, but just all things considered, we couldn't do it. So we know how to do that measurement. I think doing the OCO2 instrument and proving that it works in space will be an important step to making the methane measurements. And we do have ideas floating around for plans to try to propose to NASA to do that. But it's also fortunate that the European community is also very active in atmospheric science, and they have instruments that will go up in a few years that also include some pretty detailed methane measurements. So I think we'll get some new insights or some new peek at things from the Europeans, and then we'll probably follow up with something in the years to come. But you're right, methane's the next gas we really got to pay attention to. It's an important gas for greenhouse effect, and the emission sources and details of where it's coming from and where it's going are also not that well known. So it's the next.
Yeah. Because the concerning thing was, I think I read only recently, is that a lot of methane is actually in the permafrost layers that are melting with climate change. So that would be useful to know where these sources are, to actually pinpoint exactly where on the landmass we're actually seeing these emissions of methane.
Right. Yeah, no, that's the thing, is carbon dioxide in a way is easy because we burn fuel that we buy and we sell, and we know a lot about these anthropogenic sources. But the methane, you've got wetlands, you've got ruminant animals, and like you say, there's a lot of information about the melting in the Arctic and the potential releases, but it's all these natural processes that we have a harder time putting our hands around.
It's fascinating.
Yeah, for sure. Somebody on Google Plus wanted to know, AQ Arnold, how long before the data from the OCO2 comes back to Earth? Are you going to start getting it right away and be able to process it from day one, or is it going to take a while to build up kind of ahead of data?
Yeah, so there'll be a few steps we have to take before we manage to have data to hand out to the public and the general, our audience. Because, number one, the instrument has to get cold. So we kind of get the spacecraft up, check out that it's working right, and then we have to cool the instrument down. And once we cool it down, we have to take a whole set of measurements and make sure it's performing just like it was the last time we looked at it on Earth. And we expect that could take a month or 2 months to do that, actually, because it's very, very precise calibration. We have to really understand the performance. And once that process is done, we start on the more detailed data analysis, but still it's likely to be the end of 2014 before I'm showing off carbon dioxide maps. So it'll take us a little time because we want to get the data right, so we really need to invest in each step and do it correctly before we release it. I know Josh and Howard are going to tell me what the heck, because I think the radar guy's a little faster than we are with their data turnaround.
How quick do you guys get data, Howard, Josh?
Well, in the case of Rapidscat, the first thing we have to do is get to the space station. That takes about 2 days after launch until we dock. And then the crew is pretty busy with some very important things right after docking. And there's some live animal experiments with mice on board and things like that they have to go through first, that they have to offload. So things take a little while. But about 5 or 6 days after launch, we get to use the robotic arm to install the payload. And we actually control that from Houston, which is kind of cool. The astronauts actually primarily are not involved, and it'll take about 1 day to install the first half of our payload, which comes out of the Dragon, gets over and installed on the end of the Columbus module, and then 2 days later we go and get the other half of our payload and attach it to the first half that we had already installed. So now we're at about launch plus 8 or 9 days, and then we will turn on the payload and we will start getting data immediately. But we also have a calibration period. We'll want to spend some time checking out the radar, comparing the data to some ground sources where we have them to make sure the calibrations are correct. And so it'll be about 30 days or so until we're able to start distributing data.
And do you get to play with the robotic arm?
I get to actually sit with the people who do get to drive the robotic arm, and we get to help them understand what they're looking at through their cameras, because we understand the payload really well. They understand the station and the arm really well. That's pretty exciting.
Wow, that's pretty cool. What a cool job that is. I was worried robots were taking our jobs, but I guess it's people controlling robots.
Yeah, we still direct them. They're not independent yet.
Josh, what about you? How long until you guys start to see results from the JSONs?
Well, the JSON is kind of an interesting case because we're doing something a little bit different here with the JSON missions. We're trying to build a long-term record for climate so that we're not just looking at sea level today. We want to know what sea level is today relative to what it was 20 years ago. So in the JSON missions, what we actually do is we fly in formation with the existing mission for about 3 to 6 months. And during this period, the two satellites are about 1 minute apart. So they fly over the same spot on the ocean about 1 minute apart, essentially measuring exactly the same conditions. And we compare the two satellites with each other and make sure we understand all the differences. Then after 3 to 6 months and a lot of analysis of this data from the science team, we will eventually move the older satellite, the older JSON mission, onto a separate track and basically double the coverage that we get of the oceans. Now, the short answer, though, to your question is it's usually only a matter of a couple of weeks. We turn on the JSON satellite, we start collecting the data, but we go through this long process of comparing it with the existing satellite in order to make sure that the integrity of this long-term record is maintained. Because, as you know, the way you really see climate change is by looking at today relative to what it was 10 years ago, 20 years ago, as long as possible, because that's when you see the clearest signal.
Yeah.
So the short answer is we get some data pretty quick, but we won't really get new, unique data for several months also.
Right, right. While we're talking about it, I like that you're talking about climate change and versus like weather pattern change, because I was out near the ocean just the other day, and it was cold. It was cold in the summertime, and some people would say like, "Oh, it snowed a lot. That's it. We're good. It's no global warming. It's snowing right now."
I can't. I mean, my air conditioner's on. I can't feel global warming at all.
Right? Exactly.
That?
So, you were saying that it's gone up how many centimeters since we started measuring?
Sorry, say the question again.
How many centimeters have the oceans risen?
It's about 6 in the last 20 years, and it's about 20 in the last 100 years. Yeah.
That seems like a lot at 2.5 centimeters an inch. That's a pretty good amount of rise.
Absolutely. Right now the rate's about an inch a decade, but the big question is, what's it going to be in the next 10 years or the following 10 years? And sea level rise, in my opinion, is one of the most, like I said before, it's one of the most powerful indicators we have of just how much we're changing the climate. But it's also a really important impact because a lot of people live near the sea. We have a lot of infrastructure. Here in California, we have million-dollar homes on the beach and the beautiful Pacific Coast Highway. We have a lot of this stuff that lives close to the sea, and as the sea rises up to meet it, we're going to begin to threaten that infrastructure. How fast is that going to happen? That's really the biggest scientific question in terms of sea level rise of the day. And it turns out a lot of the answer to that probably lies in the big ice sheets in places like Antarctica and Greenland.
Mm. What about landlocked nations? Somebody on Twitter, Arya Geen, asked how climate change affects them, like the Himalayas, for example. There's a lot of snow, there's a lot of height with those mountains. How's that affecting them for your guys' study?
Well, it's still a pretty big impact. Something like 90% or more than 90% of glaciers everywhere in the world are in retreat. Only a very small number are advancing or are basically stable. So more or less you can say that frozen water all over the planet is melting. That's as true in the Himalayas as it is in Alaska, Patagonia, Greenland, and Antarctica. So, landlocked places have glaciers as well, but really the biggest impact so far is the higher temperatures, and we experience those every day. The planet's warmed up about 1.5 degrees Fahrenheit on average, but remember, it's more in the summer, more in the day, et cetera, et cetera. You start adding that up, and they really wind up being pretty sizable changes. Here in Los Angeles, for example, we've warmed up 5 degrees in the last 100 years. So the 95-degree heat wave we used to have is now a 100-degree heat wave. So the impacts are sizable.
Yeah.
And it's the extremes as well that I find scary. It's like the outlook for the extreme weather. I mean, you're still going to have seasons. I mean, I think this is the misconception of climate change, that you're never going to have cold weather. Of course you are. But you're going to have the more extreme weather. I mean, I couldn't imagine, because I'm in Los Angeles as well. I mean, I don't think there's any doubt that, we're in a crisis here. I mean, we've got water shortages. We're basically a very stressed part of the world. And I don't know, I mean, do you get a lot of feedback from the public concerning, depending on where they're from? I mean, as Trace said, people go out and they think weather is indicative of climate change. I think it's just because it's a cool day, everything's fine. What kind of feedback do you get from the public? Because in the media, certainly science media, we get a lot of negative stuff. I mean, I certainly won't go into details of it, but there's a lot of denial, and I think that's just in human nature to try and put it to one side, trying to brush it away. I mean, it's kind of an open question to all three of you, really. I mean, what kind of feedback do you get? I mean, is it positive generally, or do you go through the mill a bit?
Well, I'll probably get in trouble for saying this, but I think the response depends more on your political location than it does on your geographic location. And that's no secret, really. But the fact of the matter is that there's a strong impulse to deny human-caused climate change because we don't have a good solution for it right now. And until we do, there'll be a lot of people that just have a hard time accepting it as real. There's a famous Mark Twain quote. I'm not going to quite get it right, but it's something like, "It's very difficult for a man to recognize the truth when his salary depends on him not understanding it." So it's a difficult thing, and you see responses from all over the spectrum, really.
Yeah. I imagine studying carbon dioxide, Annemarie, you probably get a lot of talking about this topic as well. Do you guys get good feedback from people getting excited that we're up there trying to more accurately measure this gas and greenhouse gases in general?
Well, actually, to be honest with you guys, I've been laying low and staying in the trenches for a long time, just getting our technical work done. And honestly, getting close to launch is only now that I'm really starting to try to get out there and get the message out and talk to a lot of people. So my experience has been surprisingly good so far. People are excited to hear about what we're measuring. They're interested in this question about where the carbon dioxide goes. And I haven't had too much negative feedback. So I'm hoping it stays that way for a while. I mean, I totally agree with Josh that this is an international problem. We do have some science questions outstanding, but there's no science question that is so big we shouldn't start acting right now. And we need to really start working as a coordinated international effort if we ever want to get the climate change under control. I mean, the concentrations of carbon dioxide over 400 in lots of places right now, compared to what it was before the Industrial Revolution, which was 280 parts per million. That's a huge increase. And the trajectory we're on is crazy. I don't know if we can bring up, I have this graphic that shows a time series of carbon dioxide. And if you look at the most recent decades, it's amazing how fast it's going up. And I think that kind of data just really is another strong indicator that we're making an impact, and we've got to take some responsibility and turn that curve around. So this is just showing over the last, I think it's like over 180,000 years, these are ice core records of carbon dioxide concentrations, and then here's what we've done in the Industrial Revolution. We basically look like we're scaling the wall. And and that's really well understood that we've increased these concentrations. But then the big question is, what's that mean? How's it going to change in the future? And will that curve go up even faster if the land and the oceans stop absorbing as much carbon dioxide as they do today? So I guess you asked me what the response is from the public, and so far it's been good, and I am really I'm passionate and excited about this. This is important stuff, and even if someone's not too happy, I'm going to do it.
Yeah.
Well, I remember in 2009 I was reporting on when the first mission failed. There was this outpouring of grief, because I think certainly in the science community and the general public, I mean, there is this understanding that we need these missions. We need to be tracking these greenhouse gases. We need to know the sources and the sinks. I think there is this inherent understanding that we need this. So when OCO-1 crashed, that was horrible. I just remember the feedback. I remember the comments we were getting on our articles. It was like, oh my goodness, this is like our final push to try and solve this massive global problem we've got, and it's crashed. It was. I'm just amazed that you guys were able to turn it around again within 5 years. I mean, was that a real tough job? I mean, we kind of touched on it briefly, but was it kind of hard to actually convince the powers that be to put funding into a second mission, or was it just like a slam dunk because you sold it so well with the first mission?
Yeah, I mean, I think it's always a big effort, because you think about our federal budget and NASA's budget, right? There's not an extra couple $100 million sitting around in NASA's budget. So when they make a decision to do something like this, it's always a trade-off with other things. But I agree with you, especially in 2009. In the U.S., we had a lot of momentum with discussions about carbon dioxide and climate. It was actually, I think, a little bit of a more positive atmosphere. And the science community really came together and articulated the need. And so with that and the support of NASA and administration that was supportive, we managed to bring all those pieces together. And I think that, that it worked for us that time. There's no guarantee if something fails that you're going to get back on the blocks. It worked for us, and that was a really good thing. And the 5 years, actually, we could have had this baby up there like a year ago. We actually got the instrument built quite quickly. The spacecraft was coming along, but we had to wait for a rocket because we failed on what's known as a Taurus XL, and a second NASA mission failed on that same rocket after us. And so once that happened, they said, we're not going to use that for OCO. We're going to get what's called a Delta II, a big rocket that's been used a lot. So that added a little timeline to our work. So we're 5 years in part because we had to wait for the rocket. So it was a pretty quick turnaround, and we're so happy to be here, just not even a week away. Awesome.
Yeah, that's so exciting. Cool. So I did want to say, Josh, as a climate scientist, how did you get a job with the National Aeronautics and Space Administration? There's not National Aeronautics, Space, and Ocean. Or so what is it? The ocean? It's obviously very important for climate science. How did NASA become interested in the ocean, I guess?
Well, I ask myself that same question. How do I have a job here pretty much every day? I think there's a long history, actually, not reasonably long now, stretching back to the mid-'80s of collaboration and a beginning of NASA's foray into oceanography, I would say. And in fact, actually, QuickScat in large measure is just as important to oceanography as it is to atmospheric science as well. So it too is in a lot of ways sort of an oceanographic directed mission. But back in the mid-'80s, there were a lot of Earth science missions. There was a strong push to begin to, as you say, turn the camera away from the stars and toward the Earth. And Jason was a part of that, and actually its predecessor, which was called Topex Poseidon. And this actually is an interesting history. It's the first mission that was done jointly with the French space agency, CNES. And every Topex and Jason mission since that time has been a joint endeavor between NASA and CNES. And in the last two cases, also adding NOAA and the EUMETSAT, which is the European Meteorological Satellite entity. And so there's this interesting history going back of this collaboration between U.S. and French partners, and really beginning to look at the Earth in more detail. And as I said earlier, right at the top, as soon as you look at the Earth from space, you realize one thing, and that's that 2/3 of it is not Earth, it's water, it's ocean. In fact, I think it was Isaac Asimov once famously said that we misnamed our planet. It shouldn't be Earth, it should be planet ocean. And so really it's quite a natural thing once you start doing Earth science to begin to look at the oceans. And oceanography, the height of the ocean turns out to be kind of one of the most fundamental and easiest things to measure. So we've been very lucky in that regard that we've had good support from NASA and the French Space Agency for a very long time now.
Cool. And you mentioned QuickScat, and so RapidScat is just going to improve on that, right, Howard? It's going to be even more data. It's going to be more accurate data. And
yeah, very much the same data set, but of course, since unfortunately QuickScat stopped spinning 5 years ago, it doesn't give us the kind of data we want. There were other satellites that were put up, including one by the Indians, which was very successful, called OSCAT. Unfortunately, that mission failed this past February. So right now, the National Hurricane Center, the National Weather Center, the Navy, many other users and many other science communities are mourning the loss of that spacecraft and the loss of the data that it would have provided. So we're up there filling a hole that certainly exists in our national infrastructure.
Yeah, I mean, so this is one of those questions, actually, that I think we are almost accidentally addressing here, that what does space science have to do for me? Like, why should, as me on the ground? And it's like, well, is all this data shared around the world with weather patterns and organizations that tell you what it's going to be like next week? Does that all come back to kind of instruments like these?
It does. NASA has an open data policy, which means that all the data that we collect is available to the public. Some of it is in raw form, some of it is in processed data at different levels of processing, depending upon how it can be used. But we take all of our data and we put them in these distributed data archives that are located around the world. The RapidScat data goes into something called the PODAC, the Physical Oceanography Data Center. And so we'll do that. We'll take our data and just literally 24 hours after collecting it all, it gets processed and it put out in the DAC for general use by the public, for scientists. But we're also working on trying to get it to where we can get data within 3 hours to where that data can be used by the National Hurricane Center, the National Weather Center, the Navy, and other users who need much more acute data.
And there's another, if I can pipe in, another way that this data is well used by the public. So the weather is the one that's so obvious to all of us, right? We feed the satellite data and looking at the weather. But NASA also works on what we call applied sciences, and we really try to think about people who need information to make good decisions and how we can feed them the information they need. And certainly when I worked on air pollution projects, we were trying to work with air pollution control agencies and help them learn about the satellite data. And one of the cool things we might do with OCO2 is work with people who are looking at agriculture, because we have a new gem that's coming out of our data stream. A couple different science groups figured out that they can see how healthy plants are. There's actually fluorescence that comes out of the photosynthesis of plants, and we see it with OCO2. And we recently got some papers out in the literature that show how you can see crops in the fluorescence of OCO2. So we're trying to work with people who care about crops and agriculture and forest health and figure out how to feed them this information so they can use it in their decision making and in their thinking about the problems they're trying to solve. So we're always trying to reach out and find those community members and then listen to what they need to know and see if we can help them out. It's pretty interesting work.
Cool. Clayton Elder actually asked a question on Facebook specifically about that, about how does OCO2 measure that leaf fluorescence? And he asked why it's a milestone.
So it's interesting process. I mean, these plants are performing photosynthesis and they emit light. It's part, you know, they give off heat, they give off some light, and they have a chemical reaction that goes. And it turns out that just about 1% of the light that we measure up in space comes from the plants when there's a lot of photosynthesis. And it's something people have known about. They've understood how plants do this, but we've never seen it in our measurements. And partly because we need to measure carbon dioxide very precisely, we have an instrument that performs so well, you can see that fluorescence. And a couple scientists knew about this was happening. We were working with some Japanese data to practice for OCO2, and they found that signal in the data set. So it's kind of, the theory's been there, and now we're starting to have data that's really so good, you can make that link and find the signal.
That's so cool.
Yeah, there's a question just come up in the Q&A by 646 Klein. Interesting. I think I know the answer to somewhat part of this anyway. How can climate change and sea level rise be attributed to humans when we only have records going back maybe 100 years?
That's a great question.
And that's an open question for anybody.
Yeah.
Yeah, well, actually we have records that are a lot longer than that. That's the simple answer. It turns out that there's a recent sea level record that was created from the east coast of the United States in I think it was North Carolina, where they were able to reconstruct 2,000 years of sea level rise based on looking at little critters that lived at various places in the tidal zone. So this particular place had uplift, and the land there has been rising, and as it does, the sea level retreats down the slope of the beach, and you can date these little critters, how long ago they lived, and where they were in the tidal zone, and by drilling a bunch of cores, you can actually reconstruct the history of sea level off the coast of North Carolina for 2,000 years. And when you do this, what you see is that we've had about 2,000 years of utterly stable sea level, a few small ups and downs, and then in the last 150 years, during the warming, you see an incredible quick rise of sea level, 10 times faster than anything else, or several times faster at least, than anything else in the last 2,000 years. So we know that we've been in a very stable climate for the last several thousand years from things like sea level records, but we know this from also ice cores, which go back hundreds of thousands of years, which tell us not only carbon dioxide, like Annemarie showed us earlier, but also the temperature of the air at the time. And we can see that really what's happened was we were in a very warm and stable climate for about the last 10,000 years. It's during this time that civilization began, that farming began, that we began to develop technology, settle into kind of nations and states, and ultimately develop iPhones and Twitter. And really, it was the stable climate that allowed us to do that. And now what we're looking at in the future is this rapid change in the climate that of the climate that we built our civilization around. So partly you can look at the timing, but there's a long list of other pieces of evidence. Really, everywhere you look in the climate system, you can see the impact of mankind's addition of carbon dioxide to the atmosphere. You can see it in really all kinds of records. So there's a long line of evidence to show that it's human caused.
Yeah. Although, like you said earlier, that can be very difficult to grasp for people because it is such a giant, daunting problem. We got another question from Austin Wu, which is a little bit of a downer, but not really. I hope not, anyway. And that is, even if there was a solution tomorrow, he didn't say that. I'm adding that. But could we solve or halt climate change? Could it be reversed at this point? And that's, I don't know. What do you guys think?
So if you look at the carbon dioxide that we send up in the atmosphere, it lasts a really long time. So even if we shut off all our emissions tomorrow, everything wouldn't go back immediately, right? There's a long time lag before that would happen. And so but I don't think that should discourage us and make us think, oh, I don't have to do anything, because there's two other important considerations. One is, how much temperature change can we adapt to, right? And it's probably easier for us to adjust our energy systems, our agriculture, adjust to the water supply changes if there's a limited temperature increase as compared to a really big increase. So, we do want to limit the carbon dioxide as much as we can, even if we can't get it shut off today, just to minimize the effects. And the real challenge is, how do we adapt to the changes that we know are going to happen in the future, and do those changes kind of settle down in 50 or 100 years, or are we going to behave in such a way that will impact people in 200, 250 years beyond us? It's sort of, you got to get out of your head and worry about today and think about what's happening a long, long time down the road, and what do you want to do to the future generations?
I like to say it's a question of whether you want to be hit in the head by a fastball or by a wiffle ball. And I always choose the wiffle ball because it hurts less.
Good decision, Josh.
Well, on that note, and unless anybody has anything else they wanted to add that we didn't get to, I think we've satisfied most all of our questions, and we've wasted another perfectly good hour, as they say on NPR. We're used to, I guess. The show's not even on anymore, sadly. But I wanted to say thanks to everybody for coming. You guys were great. It was great to talk to you all. Thanks for watching this month's... Oh, of course, yeah. Anytime.
Thank you, guys.
Yeah, and thanks for watching this month's Space Out, everybody, in the chat rooms there. You can find NASA JPL on Twitter. They're at NASA JPL. We are at DNews. Ian is at Astro Engine. We've got Twitters all over the place. Subscribe to DNews on YouTube, please. We do science videos every day of the week. You can follow us on Google+. You can follow NASA JPL on Google+. They also have a YouTube page. We are very social up in these groups. So come and find us if you want more stories, you want more videos, you want more science. We got it. And next month's Space Hangout, Space Out, we were talking in Howard Tuesday. That's today, right? It's the 1 year for the Curiosity rover today. Is that right?
Martian year.
Yeah.
One Martian year. And one soul. It's Happy Soul Day.
One soul.
Right. Team is very excited.
Yeah, so maybe next month we should talk a bit about Curiosity, right, Ian? What do you think?
Please, yes,
yeah,
space.
I think it would be so good. So maybe I guess that'll be our tease for next month, guys. We'll see you then. And you can find us again, like I said, Twitter, Facebook. Come say hi. Thanks a lot for watching, everybody. And thanks to Annemarie, Howard, and Josh.
Thanks, everybody.
Bye, guys.
Thank you, guys.